Okay, as part of the statics of rigid bodies course, we're going to discuss changing line of action of a force. So when you say changing line of action of a force, is that for a certain force, it always has its own line of action. But we could actually transfer its line of action to, we could change it or transfer it into um, another point which is outside its original line of action. So for example here, we have an original force wherein its line of action is this one, okay, and one of its points is point B, and then we could actually transfer this line of action to this point A. Okay, so what we do for us to be able to transfer this force from point B to point A is that we will just simply transfer, or we will simply draw another force vector at this point, which has the same magnitude as that of the original and the same direction, but we'll have to negate that so that it's like nothing happened. Okay, so we have this force F, same direction as that of the original one, and of course same magnitude, but at the same time we'll have to negate that by drawing another force vector, same magnitude but opposite in direction. And of course, with parallel line of action. Okay, so what happens is that as you can see, we are able to form a couple. Okay, this one. This is a couple. Okay, so what happened is that uh, this situation is just equal to this one, because since we have negated this new force that we have formed here with this force, it's like this is nothing, and then of course this two is equal. Now with this, we could see that there is a couple formed. Okay, and as you can see, this original force F and this one that is used to negate this transferred force, they form a couple. They are parallel in direction, and then they have the same magnitude but opposite in direction. So with this identified couple, what happened is that we now have this equivalent force couple moment, such that it means that if you are going to transfer a force vector from one point to the other, or from one line of action to the other, you simply transfer the force, and then there is a couple form, and this couple is what you call the couple of transfer. Now, by principle, if you're going to transfer a force from one line of action to another, simply transfer it, and then there is a couple of transfer that will be formed. Okay, and with this couple formed, so of course the couple moment of this one is simply the magnitude of the force times their perpendicular distance. So this couple of transfer now that was formed by transferring F from point B to point A is CT. So CT symbolizes couple of transfer. That's of course equal to the force F, magnitude of the force that we transferred, times the perpendicular distance from the original point to the transfer point A. So this original force, okay, this original force, line of action of the force, is just equal to the one transferred at another point A, and plus a couple of transfer formed. Okay, so this is its equivalent force couple system. Therefore, we have what you call a couple of transfer, CT. It's the moment of the original force acting at point B, so B represents the original point about the transfer point A. Okay, such that generally, if say we have this plane system, then we have a force acting at point B, okay, this force vector, such that if you're going to transfer it from this point to this point, point A, we simply transfer that point, but there is a couple of transfer that is formed such that this couple of transfer is the moment of this force from point B, its moment about the transfer point A, such that if we have what we call the position vector from the moment center or from the transfer point to that point B, original point of the first vector F, position vector R cross F vector, that is now the couple of transfer formed when you transfer force F from B to A. So this is now the equivalent force couple system. Now, we have successfully transferred F from point B to point A, plus there is a couple of transfer formed. Okay, so that's what happens if we are going to change the line of action of a force from one line of action to another. Okay, let's have an example. So for the machine part shown in the figure, replace the applied load of 150 kilonewtons acting at point A. So as you can see here in the figure, we have force 150 kilonewtons. It's acting here at point A. Okay, we have to replace this with an equivalent force couple system with the force acting at point B. So what will happen is that 150 kilonewton load, we will have to transfer it from this point to point B, such that when we are going to transfer it, expect that there will be a couple of transfer that will be formed. Okay, so again, if we're going to transfer the line of action of a force, okay, so this is what will happen. All right, so this is our point A, and this is the original point of action of the 150 kilonewton load, whose direction is horizontal. Then we're going to have to transfer that here at point B, okay, such that we simply transfer it here. I'm going to draw it here, but we'll have to negate this also so that it seems like nothing happened, because the resultant of this two is 0. So it's just like the same as with this original force or with this one, because this is equal to 0, the resultant of the two. Okay, so with this, we are able to form a couple. So this one, this is a couple. Okay, they have the same magnitude but opposite in direction, and their lines of actions are parallel, of course. So with this, we have now a couple. With this couple formed, the couple moment would be equal to, of course, the similar force. You already know the definition of a couple or the magnitude of a couple. That is equal to the, okay, couple of transfer. Okay, that's the force, similar force magnitude times their perpendicular distance d. Okay, so from the original drawing there, this is their perpendicular distance from point A to point B. Okay, that would be 80 plus 140, or that would be 120 mm. Therefore, this is 120 mm. Alright, so therefore it's now equal to this one. Okay, we'll have to draw it to another side of the paper. Okay, so it would now look like this. So 150 kilonewton force is already here at point B, which we have transferred from point A. Okay, it's now already at point B, and plus there is a couple of transfer formed. So this is our couple formed. This is the couple formed. So as you can see, the rotation is clockwise. Okay, so that we will, the symbol that we are going to draw is of course, a clockwise couple. So this is the couple of transfer formed. Remember, by the way, that couples are transferable. Okay, or they are free to be transferred to whichever point, and the effect is the same. So couple of transfer now, we have the 150 kilonewton force times the perpendicular distance from point A to point B, which is 120 mm. Okay, so we have the 150 times 120 mm, that's 18,000. Okay, 18,000 kilonewton mm, or that would be 18 kilonewton meters. Okay, so this force couple system is equivalent to our original force system as given by the problem, which is the 150 kilonewton load is acting at point A. Okay, so this original system has this equivalent force couple system. So what happened is we transferred the 150 kilonewton force from point A to point B, and plus there is a couple of transfer formed because of that transfer of the force. Okay, then our next follow-up question is, what if we are going to replace this system? Okay, this system, we're going to replace it with two horizontal forces, one acting at point B and the other acting at point C. Okay, so instead of having this force couple system, what if we replace this original system with two horizontal forces, one acting at B and one acting at point C? So here is point B, here is point C. Okay, now one is acting here, one force is acting here, and the other force is acting here. Okay, so since we could actually refer to this force couple system, we know that there is a couple formed which is equal to 18 kilonewton meters, and there is a force 150 kilonewtons. So we could retain this, of course, the 150 kilonewton force directed to the right. Okay, and for this couple of transfer, we could change it into two horizontal forces that are parallel. Of course, they are parallel, being both are horizontal, with the same magnitude but opposite in direction. So one should be okay. One should be acting at B. Let's use another color. So let us say for this couple moment, we will convert it into two horizontal forces, one acting at B and here one acting at C. So we know that the horizontal distance from B to C based on the original figure is 40. Okay, from B to C. Okay. We have here 40 mm. Okay. Now remember, the couple of transfer is equal to 18,000 kilonewton mm. Okay, so let us say what should be the one acting at B should be directed to the right, the one acting at C should be directed to the left, so that the rotation is the same as this couple transfer, which is clockwise. Okay, so the question here is, what should be the value of this force two horizontal forces in order to form a couple equivalent to this couple of transfer 18,000 kilonewton mm. Okay, so we have the couple, this two couple, this one and this one. Okay, this one pair of couple, we have their similar force times their perpendicular distance, which is 40 mm. It should be equal to this couple of transfer 18,000 kilonewton mm, such that F1 should therefore be 18,000 all over 40. We'll have here okay, so it should be, therefore it should be 450 kilonewtons. Okay, therefore if we're going to change this force system into two horizontal forces acting at point B and point C, the result would be okay, we have one acting at point B, we have the 150 kilonewton load, okay, which is this one, and then for the couple, we replace it with two forces wherein the magnitude is 450. So you have another one here, 450, still acting at point B, and another one acting at point C, which is also 450, but this time it is directed to the left. That's why with the two couples, this one 450 and 450 to the right, 450 to the left, acting at point B and point C respectively, there is a couple form to which 450 times this perpendicular distance of 40 mm, it's equal to the couple of transfer 18,000 kilonewton mm. So since these two force 150 and 450 act on the same line of action, or yes, they act on the same line of action at point B, we could just replace it as a singular horizontal force by adding the two magnitudes for 150 and 450. So finally, we now have this force system. Okay, so at point B, we have a total of 150 plus 450, that is 600 kilonewtons acting at point B, and at point C, we have 450 kilonewtons. Okay, therefore, for this original force system, its equivalent force couple system is this one. So we have the force already at B, 150 kilonewtons, and a couple of transfer, because of transferring it from point A to point B, is 18,000 kilonewton mm. But if we are going to replace this force into a force system wherein there are two horizontal forces, one acting at point B and one acting at point C, the result is this one. So one horizontal force acting at point B has a magnitude of 600 kilonewtons directed to the right, and the other directed to the left, acting at point C, having a magnitude of 450 kilonewtons. So this one is equal to this one, which is also equal to this one. Okay. So let's have another example regarding changing line of action of a force. So next example. Okay, we have here, we are going to replace the force couple system here, this is shown in the figure, with an equivalent force couple system with the force acting at point A. Therefore, as you can see in the figure, we have this force vector and this couple vector. Now, we have to transfer this force at point A. Okay, from point of action of point B, we will transfer it to point A. Okay, now when we are going to transfer it to point A, we have to get the equivalent force couple system that is equivalent to this original system. Okay, so with this couple of transfer, with this transfer of force vector from B to A, there is a couple of transfer form. So what will happen is we now have this new system. Okay, now let me just draw it abruptly. Sorry if it's not that, like, the lines are not that straight, but at least we could just demonstrate what happens. So this, the original force is here. Now if we're going to transfer it here at point A, now this is now the new location. But again, every time you transfer a force vector from one line of action to the other, there is always a force, a couple of transfer formed. So this is, you have to imagine the plane of the common plane of force F and point A. Okay, so that with that rotation from force F to A, the couple form is the moment of the force, moment about the transfer point. So that is always, you have to remember that the couple of transfer is always equal to the force vector, it's equal to the moment of the first vector about the transfer point. Okay, so if we are going to get the moment of this force about its transfer point, which is point A, okay, the couple of transfer will look something like this. So let us say this one. Okay, this is now the couple of transfer form. But when we transferred the force F from B to A. Okay, so okay, we'll have, for this couple of transfer, we'll have R cross the force vector F. Okay, so again, couple of transfer is the moment of the force about the transfer point. Okay, so we may use position vector R. Okay, our position vector R for this formula would always be from the transfer point or moment center to any point on the original line of action of the force. So this is our force, a position vector R. Okay, that would be the position vector R that we will use, such that the couple of transfer formed is equal to, we have R cross F, and in which case our R vector would be, okay, along the y-axis the distance is 120 mm. Okay, so we have here 120 J positive. Okay, and then along the z-axis, that's 60 downward, so we have minus 60 k hat. Okay, so this is our position vector R from the transfer point to any point on the original line of action of the force vector, which we are going to transfer to point A. Okay, and then we also need, of course, the force vector F, so that we know that force vector F has a magnitude of 100. We'll multiply it to its unit vector. So for its unit vector, we will be using position vector from B to E. So for this, the x component would be 80. Right, this one, 80. Then that would be negative 80i. Okay, I hat, and for the j hat, it doesn't have a j hat because it's acting at the zx plane. Okay, and then for the k hat, this one, this distance, which is equal to 60. So we have plus 60 k hat. Okay, And then we have all over 80 squared plus 60 squared. So for the I hat, we have 100. Okay, let's just use x in the meantime. Then we'll have, or rather, we have 100, the scalar magnitude, over square root of 80 squared plus 60 squared. Okay, so for x, we'll be using, first one is negative 80. Okay, this is for here, negative 80. Right, so 80 squared, 60 squared, 100, negative 80. So still it's negative 80i. And we have plus 60 k hat. Oh, by the way, this means that square root of 80 squared plus 60 squared is actually also equal to 100. So that's why. Okay. So for a couple of transfer, we now have, okay, I, j, and k. This is cross product, remember. So for r, we have 0, I, 120j hat, negative 60k hat. For f, that's negative 80i hat, 0j hat, plus 60k hat. We have for I times 120 times 60. We will be performing basket method to get the determinant. Okay, that's 7,200. I hat. For j hat, we have negative 60 times negative 80. That's 4,800, of course. Okay, 4,800. J hat. For k hat, we have k times 0 times 0, so we have 0. For upward, we'll have negative 80 times 120 times negative 1. So that's 120 times 80. Okay, that's 9,600 k hat. Then we have 0 times 60 times I, that's 0, and then 60 times 0 times j, that is also equal to 0. So we now have this couple of transfer, and of course this is in I think that would be, since it's in newtons, and then our r is in mm. Okay, by the way, our r is in millimeters, our force is in newtons, so therefore the couple of transfer is in newton mm. Okay, and then we already have transferred force F from point B to point A, so it's already here. Okay, and with that transfer, there is a couple of transfer formed with this vectors, 7,200 I plus 4,800 J plus 9,600 K hat. That would be in Newton mm. Okay. And then of course, you already know that there is still this couple, this original couple vector directed from this directed from point D to point B. Okay, so we'll have to get its vector notation first. So for the original couple vector C, okay, the magnitude given is 3,600. We have, this is in Newton mm. And then we'll have to multiply it to its lambda or unit vector. So for its unit vector, we will be using the position vector from D to B. Okay, so we'll have 3,600 now, and then the I hat for distance D to B would be 80 mm. So 80 I hat For j hat, that would be from this distance, which is 120, so it's also positive 120 j hat. And then for k hat, we have the downward distance, this one, okay, which is 60. So since it's downward, we have negative 60 k hat over its magnitude, 80 squared plus 120 squared plus 60 squared. So c vector therefore is equal to, we have 3600, then we'll have x, then we have square root of square root of 80 squared plus 60 squared plus 120 squared. Is that right? 80, 120, and 60. Okay, and then first we'll have 80i, so we'll have x as 80. Okay, that would be 1843.73, 1843.73 I hat. For the j hat, we'll have 120 as the value of x. 2765.6 j hat, and then minus, we'll go with 60. Okay, 1382.8 k hat. Okay, we are now done. We have the couple c vector, we have the f vector, and then we have the couple of transfer ct, because we transferred this force vector from point B to point A. So therefore, the equivalent force couple system is, we have, of course, the force F, vector notation is negative 80 I hat plus 60 k hat. This is in newtons. And for the couple, resultant couple, we'll just sum up all of the couple moments. So we have the couple of transfer plus the couple C given. So 7,000, okay, plus 1843.73 for the I hat. Okay. For the j hat, we have 4,800 plus j hat for the couple C, 2765.6. That's for the j hat. And then for the k hat, for the couple resultant, we'll have a couple of transfer, that's 9,600. But for the couple C, negative 1382.8. Okay, and that is for k hat. Okay, so we'll have now here the couple of couple resultant. Having two couples, we get the resultant by adding the two couples. So this is the result. We have for I hat 7,200 plus 1843.73. It's 9043.73. I hat plus for the j hat 4,800 plus 2765.6. Okay, that's 7565.6. Okay, 7565.6. That would be j hat. Then for k hat, we'll be adding 9,600 minus 1382.8. That would be 8217.2. 8217.2 k hat. This is of course in Newton mm. So what the problem wants us to do is we will replace this original force couple system. This is called force couple system because this system contains a force vector and a couple vector. Now we have to replace it with an equivalent force couple system wherein this force vector F acting at point B is transferred at point A. So with that transfer, since we transfer it here at point A, always when we transfer force vectors from one point to the other, changing its line of action, there is always a couple of transfer form. And always remember that the couple of transfer is the moment of the original force about the transfer point. So since our transfer point here is point A here, okay, then the couple of transfer form is the moment of this original force to or about the transfer point A. So since this is the moment center or the transfer point, the R vector, position vector, should be from the transfer point to any point on the original line of action of the force vector F given. So this is the R position vector used, such that the couple of transfer is we have this R vector cross the force vector that we are going to transfer. So the result is this one. So we now have a couple of transfer aside from this original force couple vector C. And then with the couple vector C, we also obtained its vector notation, such that we now have one force and then we have two couples, the couple of transfer and the original couple vector C. So we have this, the resultant force is simply there, since there is just one force. So technically force vector F is already the resultant force. And then for the couple resultant with the two couples, we just add the two. So remember that whenever you add vectors, you add individually the x and y and z components. So what happened here is that for transfer couple I hat 7200, we added it with the I hat of couple vector C. The same with the J hat and K hat, individually adding. So this is now the equivalent force couple system if we change this one with this one. Okay, so that's it. Thank you.